Good day, everybody. I am Hong Wu. I am doctor and associate professor in civil engineering. I'm pleased to provide to you the lecture course Structural Design Review. This course is a part of the series of FE Civil Review session. Here are my address, email, and my office number. When you have a question related to this course, you can contact to me. In this slide, I present to you the exam, content, and reference. This course covers two undergraduate level courses of MSU and CEE. The first course is the design of concrete structure, and the second course is the design of steel structure. Here are 5 documentation of reference that I have used for the presentation that you see in the next slide. When you have more time, you can see the detail inside 5 documents that I present to you in this slide. In my presentation, I will put the number of the chapter according to the book FE Civil Review of the author Lindeberg. The chapter of this presentation will vary from 37 up to 47. You do attention that for each chapter there are remainder part of the theory, and then there are exam like example problems and sample question with step-by-step solution. I have designed this course for reinforcing the theory and the application of fundamental concepts for the structural design. So in this slide, I will present to you the first practical problem related to the cementitious material. In this practical problem, the question is that which is the following statement are true about fly ash? You can see firstly the question, the statement from 1 to 4, and you can see on the documentation that fly ash reacts with the calcium hydroxide to increase bendings, acts a microfiller between cement particles to increase strength and durability while decreasing permeability and enhances resistance to scaling from raw decising chemical when it meets ASTM C618 and is used a replacement for less than 45% of the Portland cement. And you do attention that the calcium silicate hydrate is a bundle that holds concrete together on its ours. So when you can see the theory and you see the statement written here, you can see that the good answer is C, with the good statement 1, 3, and 4. Now, we pass in the second practice problem. You can see in the question in the practice problem that they ask the question, which of the following criteria must be met in order for the compressive strength of concrete to be certified? And you can see that they give 4 statements varying from 1 to 4, and after they give 4 options A, B, C, D. What is the good question? So you can see in the documentation the good theory and the documentation show that the compressive trend of concrete is considered satisfactory if two criteria are met. The first criteria is no single trend test falls below the specified compressive trend F prime sub C by more than 0.01 F prime sub C. And the second criteria is that the average of every 3 consecutive trend tests equals or exceeds the specified compressive trend. So you can see the theory as you compare this theory with the option that you can choose. And the good question is that the statement 1, this one, and 3, this one, are correct. So the good answer for this practice problem is A. Now, in this slide, I will present to you the theory about the modulus of elasticity of concrete. So, in this figure, you can see the typical concrete stress trend curve for different concrete with the trend varying from 2000 psi up to 6000 psi. This curve, this diagram show the compressive stress in function of the trend, and you can see in the right of this slide one diagram showing the relation between the compressive stress and the trend for one typical concrete. And you can see that there are different modulus, and the modulus of elasticity of concrete is defined as the ratio of stress to trend in the elastic region. And you can see on the ACI 318 the definition of the second modulus of elasticity. And I show you in this slide two equations for calculating the second modulus of elasticity of concrete. The first equation is valid for the international system units, and the second equation is valid for the United States unit. And in this slide, I will present to you the practice problem related to the modulus of elasticity of concrete. The question of the problem is that which statement about the modulus of elasticity is true. So you have here 4 possible response, and you can see in the documentation that the modulus of elasticity is the slope of the stress trend diagram in the linearly elastic region. So you can compare with the different solution proposed. You can see that the good question, the good answer is B. And now I present to you in this slide the second practice problem. The question of this problem is that what modulus of elasticity is predicted for the normal weight concrete with a compressive trend of 3000 lbf per inch square. And you can see the corresponding equation that I have present to you before. You can apply this equation and you replace the value of parameter W C and F prime sub C, and finally you can find the value for the EC. This value equal to 3.2 times 10 6 psi. So you can see that the good response for this problem is D. Now we pass in another practice problem. The question is that which category of steel contain 0.15 to 0.29% carbon. And you can see the response expansion of the theory that you can find in the documentation. Carbon steel are divided into 4 categories based on the percentage of carbon: low carbon, less than 0.15%, middle carbon with the percentage varying from 0.15 up to 0.29%. And after you have another category, medium carbon and high carbon. And when you can see the question between 0.15 up to 0.29% of carbon, you can see that the good answer for this problem is B, mid carbon. Now I show you in this slide the steel properties. So on the left of this slide, I show you some typical stress strain curve for structural steel for 3 types the steel different, that is different. The first one it is for heat treat construction alloy steel, and the second one it is a high strength low alloy carbon steel, and the last one it is carbon steel A36. This diagram show the relation between the stress and strain of 3 steel that are different. And on the right of this slide, I show you one diagram of one typical steel. So you can see here 2 curves, and you can see here 2 value of axis X. So the upper data correspond to the upper curve, and the lower data correspond to the under curve. Now we can pass in the practice problem. The question is that which property of steel allows it to undergo large in elastic deformation without fracture. And you can see on the theory that the yield stress is the unit tension stress at which the stress strain curve exhibits a well-defined increase in trend without an increase in stress. And after, the modulus of elasticity is the slope of the initial trend line portion of the stress trend diagram. Doubly is the ability of a specimen to absorb energy. And after, you can see that the ductility is the ability of steel to undergo large inelastic deformations without fracture. So when you compare the theory with the possible solution, you can see that the good answer for this practical problem is C, ductility. Now, I show you in this slide a reminder about the service load, factor, the lows and low combination. So in this slide, I show you some combination of the load combination. When that and lever load only are considered, you can apply the equation. And when the dead and lever load and wind are considered, you can apply the equation. And finally, when earthquake force are considered, you can apply the equation. You know that Q is the required trend, D is the dead load, L is the live load, and E is the earthquake, and W is the wide load. In this slide, I would like to show you that the design trend is the result of multiplying the nominal trend by a trend reduction factor phi. So the design trend is equal to phi times nominal trend. So the design criteria for all section in a beam are phi times m n d is superior to m use, and phi v sub n is superior to v use. And the table, I would like to show you some trend reduction factor phi for some common cases. So you can see in detail in the table. Now, in this slide, I will show you one practice problem. Here is the question of the problem. So, assembly supported reinforced concrete beam 12 in wide and 28 in depth span 20 feet. We know that the beam is subjective to a uniform service dead load equal to 2 kips per feet and to a uniform service lever load of 2 kips per feet. The question is that what is the factor the uniform load in this case? So for answer for the question given in the practice problem, you can firstly you can calculate the weight of the beam per unit length by this equation. W equal to B H W. and you can find the result. W equal to 0.35 kip per feet. And after, you can apply the equation for calculating the factor uniform load. This uniform load is the maximum of two equations. The first equation is that U equal to 1.4 D, and the second equation is U equal to the 1.2 D plus 1.6 L, and you can replace the value of D and L, so you can find the solution. The larger value control between two values that you have calculate is that E 6.7 kip per feet. So you compare the power value with the solution proposed, so that you can see the good answer in this case is 6.7 kip per feet. Now, I would like to show you a reminder about the steel reinforcing and type of beam cross section. This figure shows some typical reinforcement in beam. You can see that in the first figure, there is longitudinal reinforcement for the bending loading, and they also stirrup for the shear trend. And sometimes we need to deform the longitudinal reinforcement steel for the bending loading. And this figure I show you a slab beam floor system, and you can see the moment diagram for this slab beam floor system. And here you can see the section AA, and you can see that in this case the compression zone is in the lower of the beam, and the compressive and in the tension zone is on the upper of the section of the beam. And for the section BB, you can see that the compression zone is in the upper part of the beam, and the tension zone is on the lower part of the beam. So in this slide, I would like to show you some equation for calculation the minimum and the maximum steel area. Firstly, for this slide, I show you the equation for the calculation the minimum steel area. You can see here there are two equations. The first one, you apply with the international system units, and the second he applied for the United States units. You can see also there are another equation for calculate the minimum steel area. So you do attention that the minimum steel provision of the equation 15.13 and the equation 15.14 do not have to be followed if the area of steel provided exceeds the calculated amount requirement by at least 30% according to the ACI 318 section 10.5.3. Now, in this slide, I would like to show you the equation for calculating the maximum steel area. Okay, I show you in this slide some step for calculate different section of steel. You can see here the different equation for calculate the maximum steel area, and in the figure that I show you in the right of this slide, it show the beam at balanced condition. So you can see that the upper zone is the compressive zone of the section of the beam, and the lower part of this section is the tensile zone of the section. And here is the trend diagram between the trend given by steel and the trend given by the concrete. And I show you here the equation for calculate the factor beta 1. And you do attention that the what is the beta 1? The beta 1 it is the ratio between AB and CB. And you know that AB equal to beta 1 times CB. It is the compressive zone of the beam. And here are different value of beta 1 in function of the value of trend of concrete. And when you combine the equation 15.16, this one, and 15.7, this one, you can calculate the balanced steel area. And this equation show the relation between the balanced steel area and function of the beta 1 F prime sub C F Y, and B it is the width of the beam, and D it is the effective height of the beam. So you have a two equation. The first one is established according to the international system units, and the second one is established according to the United States units. And in this slide, I would like to show you some parameter and some diagram apply for the design of reinforced concrete beam. For the first case here, it is the case of singly reinforced beam. And you can see here the internal force and trend for a beam, and this one show the trend condition, and this part show the resistance factor phi for some common cases. For example, for tension control section, you can take phi equal to 0.9, and for the compressed control section member with the tie reinforcement, you can take phi equal to 0.65. And for the other case, you can see in detail. And this table show the ASTM standard reinforcing bar with different parameters, bar size, diameter, area, weight. And this one show different parameters that you can use for the design of singly reinforced beam. In this slide, I will show you some steps for the design of singly reinforced beam. This figure show you the condition at maximum moment, and the first one show you the trend distribution of the beam, and the second show the compressive stress distribution for the compressive zone and for the tensile force given the steel bar, and this diagram show the equivalent rectangular compressive stress block that you use for the calculation. It show that you can, based on the height PT1 times C for the compressive zone of the concrete. And here are different steps that you can follow for calculate the nominal moment capacity. You can note that the nominal moment capacity is dependent of the steel area section, the strength of the steel Fy, and after the effective height of the beam, and lambda. Okay, and lambda you can find in the equation that show in different steps of this slide. Now I show you in this slide the practical problems. So you can see here the figure of the problem. You can see that the problem gives you the span length and the cross section of the reinforced concrete beam, and they give you different property of concrete and reinforcing steel property. And the question is that what is the maximum allowed lever load for this beam PL? So for answer the practical problem, I show you here the condition at maximum moment that you have seen before, and I can establish different equation. Different equation between the ratio epsilon t per epsilon c. You can see based on this diagram, you can establish the ratio between epsilon t per epsilon c. And after, from this equation, you can calculate the ratio d per c in function of the fc, ft, and fc. Epsilon c is the deformation of the concrete. Epsilon sub t is the deformation of the steel bar. And from this equation, you can calculate the ratio c per dt in function of different value fc, epsilon c, fy, and e. And finally, you can find the ratio between 1 per dt. A function that is a function of c and F sub Y, and after you can calculate the nominal moment trend by this equation, and from the equation you can calculate AS, it is the area of steel bar, and after because A equal to F, beta 1 C, so you can see here beta 1 times C, beta 1 times C equal to 8. See it height. It is the compressive zone of the compressive concrete for the equivalent rectangular compressive thread block. So from that you can find the equation of AC. Pardon. And after you can calculate the balance reinforcement ratio Rho sub B by this equation, and finally you replace the value of parameter that you did, and you can find the result of Rho sub B equal to 0.0456. So when you compare the final result with the different solution, you can see that the good response for this practice problem is B, 0.046. Now I show you in this slide some steps for the design of doubly reinforced beam. So I show you in this slide the procedure for calculating the nominal moment capacity of a doubly reinforced beam section with a no shape and reinforcement. You can follow the step written in this slide from step 1 up to step 8. So you can calculate the moment, the nominal moment capacity in function of different parameters written in this equation. So now we pass in the next slide. In this slide, I show you some equation for the design of doubly reinforced section. This column, I show you the equation for calculate the nominal moment stress of the beam for the case that the compressive steel use. And for the case of the from the case that the compression steel does not use, you can apply the equation for calculate the nominal moment trend of the beam. So in this slide, I will show you the practice problem. What is the question? You can see here the data, the input data of the problem. The cross section of the reinforced concrete beam with compressive reinforcement is shown in the figure with different property of the concrete and the steel. And the question is what is the nominal moment capacity of the beam? So for answer this question, you can see here the step for finding the result. Firstly, you calculate to know if the compression steel used. You calculate the difference between A sub S minus A prime sub S. You can find that the difference is 2 in square. And after you can calculate to know the value that you can find here. You can find here that AS minus A prime sub S is superior to 2.2.2 in square given by this equation. So from this equation, you can conclude that the compression still use. So now you can calculate the depth of the compressive thread block 8 by this equation, and you can find the final result for 8. And after, you can calculate the nominal moment trend by this equation given by the theory. And finally, you can find the solution and the result for the nominal moment trend. Mn equal to 187 feet times Gibbs. So you compare with the option in the practice problem, you can find that the good answer is D. Now, in this slide, I will show you the design of the reinforced T-beam. So the most important is that the effective width BE for a T-beam is the minimum of 1/4 of the beam's span length, or the stem width plus 16 times the thickness of the slab or the beam spacing. So if you will show an effective flank width of a T-beam, BE and BW. So the design moment trend of the T-beam is contingent on the value of A shown in the following equation. So you can calculate A by the equation, and after, if A is inferior to HF, you can calculate AS max and MN, and if A is superior to HF, you can calculate A sub S maximum and MN following two equations written in this slide. So now I show you the practice problem for the T-beam. So you can see the figure showing the flow system consists of 10 30 feet long reinforced concrete beam and a continuous 5-inch deck slab. We assume that the beam are under reinforced. The question is that for each beam in the floor system, what is the ACI specified effective top flank width? So you can see the solution written in this in the right of this slide. You know that the effective flank width EBE, it is the smallest value between three equations. The first equation equal to 1/4 span length. The second equation equal to the sum of BW and 6 times H sub F. And the last equation equal to the beam center line spacing. So when you calculate the value for three equations, you can find that the effective flange width is 50 inch. 50 inch. So you can compare the final result with the option that you can choose. So the answer is B, 50 inch. Now I show you the second practical problem. You can see the similar problem with the flow system, with the deck slab 4 in and the height 22 inch. And in the problem, they give you the property of the concrete and the steel and the sample span length. The question is that which is the nominal moment capacity of each beam based on ACI trend design. So for answer this question, I show you here the solution. So you can calculate firstly the depth of the concrete compressive stress block A by this equation, and you can find A, the value of A, and after you can apply this equation for calculate the nominal moment capacity Mn, and you can find that the value of Mn equal to 525 kips. So you can see that the good answer is C. And I show you here another practical problem that is similar that two problem that you have seen before. They give you some input data for the floor system. They give you the property of the concrete and the steel, and they ask you the question about the nominal moment capacity of each beam. And I show you the solution in this slide. So you can see the detail when you have more times. So firstly, you can calculate the depth of the concrete compressive stress block A by this equation. You can find A equal to 3.55 inch. And after you can follow some equation for calculate the AR and AF. Okay. You know that AF is the area of overhanging flange. AC is the total area of concrete compressive stress block. AR is the area of concrete compressive stress block in the rectangular part of the T-beam between the overhanging flange. AF is calculated by this equation, BC minus BW, and on this group, the difference between BC minus BW times hash sub f, and you can calculate, you can find the value of AF, and after that you apply the equilibrium of horizontal forces. You can calculate A, and from the value of A you can calculate the value of the nominal moment capacity of the T-beam Mn by this equation. And after the detail of the calculation, you can find the value, the final value of the Mn. So when you have the final value of Mn, you can compare with the option given in the beginning. Then you can find that the good answer is B, 775 kips. So now I will pass another practice problem. So in the problem, they give you the monolithic slab beam floor system given by diffuse, and they give you the dimension of the slab beam floor. They ask what is the most nearly the effective flank width. So as you know before, you can calculate the effective width of the flank by this equation. BE is the small lead of 3 equation. I have showed you before, so you can find the effective flank width is 54 in. So the good answer is B. So I would like to show you in this slide another practice problem. Here is the input data of the practice problem. A reinforced concrete T-beam with the 30-feet span and a 30-inch effective width with a floor slab system. It fixed at both ends, and it reinforced axial in the figure, and they give you another parameter value of concrete, steel, and they give you the section of the beam. The question is that what is the nominal moment capacity in the positive moment region of the beam? So for resolving this problem, I show you here the solution. Firstly, you can calculate the distance from the extreme compression fiber to the extreme tension steel D. By this equation, you can find D equal to 27.5 in, and after you can determine the height of the thread block A by this equation, and after you can calculate the nominal moment capacity Mn by this equation, so that when you compare the result with the option, you can see that the good answer is C. And here I show you another equation using the concrete property for calculating the Mn, and we can find the same result for 2 ways of calculation. Now, in this slide, I will show you some remainder of theory related to the shear stress. I show you here typical reinforcement in beam. You can see that the stirrup can resist to the shear stress. And I show you here some typical pattern of shear cracks. And in this part, I show you the basic equation for the design for the shear force. So you can see in detail the different equation for calculate the shear strength provided by concrete VC, and after you can follow for different cases with stirrup or without stirrup. And you can see that the beam width used in the shear equation is specified by W equal to B for the rectangular beam or BW for the T-beam cases. And in this slide, I show you the equation for the calculate the beam shear capacity. And in this figure, I show you the contribution of the vertical stirrup to shear capacity. So you can see detail of the equation I give in this slide. So let's start with one particular problem for shear stress. So the cross section of the reinforced concrete beam with tension reinforcement is shown by this figure. So they give you some data about the property of the concrete, the steel, the area of the steel, and they ask the question about if the depth load shear force in the beam is 5 kip, and the lever load shear force in the beam is 15 kips, and then the minimum amount of shear reinforcement needed for a center to center stirrup spacing of 8 in based on ACI trend design is mostly what value between A, B, C, D. So I show you in the right of this slide the solution. So firstly, you can calculate the ultimate shear force in the beam value by this equation. And after that, you can calculate the nominal concrete shear strength VC by this equation. And because values is superior to phi VC per 2, so shear reinforcement is required. And after you follow the calculation given here, and you can find the required shear strength provided by steel is calculated by V sub S, and after from V sub S you can calculate the required steel area A sub V by this equation, and after you can compare the final result with the option given in the beginning. You can find that the good answer is 0.14. So it is very close of the AV that you can find in this equation. Now we can pass in the second practice problem for the shear stress. Here is the problem. Here is the beam. They give you the span length and cross section of the reinforced concrete beam, and they give you the property of concrete and the steel, and they give you the dimension of the section of the beam, and the beam support concentrated lever load of 15,000 lbf. So the question is that the minimum amount of shear reinforcement required for a center-to-center stirrup spacing of 12 in under ACI trend design specification is mostly nearly one of the A, B, C, D. So here is the solution for the practice problem. You can calculate firstly the value of V used by this equation, and after you can calculate the nominal concrete shear strength VC by this equation, and after you can find that VU is superior to V times VC per 2. So you can find that the shear reinforcement is required. And after you calculate AV by this equation, and from this one you can calculate the amount of shear reinforcement based on factor loading by this equation, and finally you can find the value of A sub V. The final result of A sub V is equal to 0.376 inch square. So when you compare the final result with the option given in the beginning, you can see that the good answer is C. So now I would like to pass in the next chapter concerning the reinforced concrete columns. So in this slide, I show you some reminder of the theory related to the reinforcement concrete column. So you can show, you can see in detail when you have more times for the shock reinforcement column. You can apply the column longitudinal reinforcement limit PG by this equation. PG equal to AST per HG, with AST is the area of reinforcement steel and HG is area of column. So you can see in detail. And after, for the slenderness ratio, the quantity KL per R is the column slenderness ratio. So the columns that are part of braces structure are considered to be short columns if the equation holds, and given by this equation, KL per R is inferior to 34 minus 12 M1 per M2. And here I detail the significance of different parameters in this equation. And in this slide, I show you the different shock reinforcement concrete column for tire column in this part, and for spiral column in this part. And I give in this slide the equation for calculate the axial compressive load capacity for design of the tie column according the equation. And for the spiral column, you can apply the equation for the the calculation of the axial compressive load capacity. And I show you in this slide the axial, the relation between axial load in function of the bending moment M. And I show you here the axial load PO in function of different parameters F prime C, AG, AST, and FY. And this figure show the relationship between nominal and desired interaction diagram. And equation for the finding the end moment due to the fixed end or eccentric loading, Mn equal to M2 or Mn equal to Pu times E. And for the long reinforcement concrete column, you can apply the equation given in this slide. You do attention that column that is a part of the braced structure are considered to be long columns if the equation hold the ETA equation. And here is the figure showing the braced and unbraced frame. First case is for the frame braced by one, and the second case for the unbraced frame. And here is the critical load or earthly load for the long reinforcement concrete column. And this critical load depends on E, I, K, L. I note here the significance of different parameters of this equation. So now I show you the practice problem for the design of shock column. Here is the problem for the shock column. They give you the apply axial dead load and the apply axial lever load. They give you also the property of concrete, the property of steel, and the dimension of the column. They ask you the question, what is the minimum required size of each longitudinal reinforcing bar? And you can choose some option given in the problem. And for the detail of the solution, you can see when you have more times. So I just talk very shortly the step so that you can apply for the solution. You calculate firstly the minimum area of reinforcing steel AS by this equation. After, you can determine the required amount of reinforcing steel by this equation Pu. And after you can calculate the nominal axial compressive load capacity by this equation. Okay. And after, finally, you can calculate the area of longitudinal reinforcing steel AS given by this equation. And finally, you can calculate the requirement, the required area of each longitudinal reinforcing bar by this equation. And you can find the solution that A equal to 1.64 inch square by bar. So you know that bar area of 1.64 inch square is satisfied by a number 14 bar. So the good response in this problem is D, the response D. Now I just show you in this slide the second party problem. They give you the apply axial dead load and the apply axial lever load with the property of the concrete and the steel, the dimension of the column. They ask you the minimum required size of each longitudinal reinforcing bar. So you can apply the similar step that you have seen in the previous practice problem. You can calculate by step AS, PUs, PN, AS, and finally you can find the required area of each longitudinal reinforcing bar by this equation. So A equal to O for 0.405 inch square by bar. So that you can see here the good answer is D. So I show you in this slide another practice problem. You can see in detail. Reinforced concrete tie column is subjected to a design axial compression force of 1090 kips that is concentrically applied. And they give you another parameter, a specified compressive strength, the degree of the rebar, and the specified longitudinal steel ratio. The question is that what is the most nearly the width of the slide of the smallest square column that will support the load. So the solution for this practice problem, you can calculate firstly the design strength of the column given by this equation. And from this, you calculate the specified longitudinal steel ratio of 0.02 by this equation. And after that, you can finally calculate B equal to the root square of HE, and you can calculate B equal to 19.0 8 inch. So the good answer is C. So now we can pass in the next practice problem. In this problem, they give you the 16-inch square tie column, and this column must carry 220 kip dead and 215 kip lever load. Okay, and after they give you the property of the concrete and the steel. The question is that what is the longitudinal reinforcement of this column, and they give you 4 options for answering. I show you here the solution for this problem. Firstly, you can determine the design load per use by this equation. And after, you can calculate the gross column area, HE. And after, you can calculate the capacity V times Pn max. After that, you can calculate, you can find the design criterion by this equation. Pn max is must be superior to P use. And from this equation, you can calculate the AST, and after Rho. It is the ratio between AST per HE. And the result of Rho is 0.028. So you can check the limit between the minimum value and maximum value of Rho. So you can find that the good answer is 8, 0.088 for this practice problem. Now we pass and see another practice problem. An 18-inch square tie column is reinforced with 12 number 9 grade 60 bars and has a concrete compressive strength of 4,000 lbf per inch square. The column with the placed against sideways has a supported height of 915 and support axial load only without end moment. The question is that what is the most nearly the desired axial load capacity? So for the solution, firstly, you can determine the effective length factor for a column placed against sideways, K, in this case, K equal to 1. And after, you can calculate the ratio, the ratios of duration R equal to 0.2088 H. And after, you can calculate the slenderness ratio by this equation, KLN per R, and you replace the value of parameter, and you can find the value of this ratio. This value equal to 20.8. And after that, you can calculate the gross area of the column, HE, by this equation, B square, and you can find the result of HE, so that the area of longitudinal steel reinforcement is calculated by this equation. A sub ST equal to LAB, and you can find that the value equal to 12 inch square. And after you can calculate the design axial load capacity of this column by this equation, and you can find the result of the problem. Phi times Pn equal to 926 kips. So when you compare the final result with the option, you can find that the good answer is 8. Now we can pass another practice problem. In this problem, they give you the number. They give you the number of the bar. The short tie column shall use a number a bars, and as we assume that the loading has a low eccentricity, and they give you the property of the concrete and the steel. The question is that what is the design strength of this column? Here are the solution. Firstly, you can calculate the gross area of the column by this equation. HE equal to P times D square sub Z per 4, and you can find the value of HE. After that, because there are a number A bars, you can calculate the area of steel by this equation. And after, you can calculate the design strength by this equation, phi Pn by this equation. And after, you can find the final result, 709.7 kips. So you compare the final result with the option. You can see that the good answer is A. So now we can pass in the next chapter. In the chapter, I just give you a reminder about the theory for the one-way slab. This is a part of the reinforced concrete slabs. In this slide, I just give you some equation for the slab design for pressure, slab design for the shear, and here is the a preview about the one-way slab, and here is the model used to obtain moment and shear for one-way slab. And this one, this table shows the minimum one-way slab thickness for different construction and minimum thickness arch. In this slide, I show you some feature showing the two-way slab, and you can see here the definition of the flat plate for two-way slab, and this one is the flat it is a flat plate, and this one quad slab for the C, and for the D it is a two-way slab with beam. So I show you in this slide one particular problem for the one-way slabs. What is the question? The question is that all the following conditions that must be satisfied in order to use the simplified method for computing shear and moment in one-way slabs given by ACI 318. The option is that A, B, C, D. And when can you see in the documentation? You can see that shear and moment in one-way slab can be computed using the simplified method specified in ACI 318. And in the section A.33, when the following conditions are satisfied: A, there are two or more spans. B, spans are approximately equal with the longer of two adjacent spans not longer than the shorter by more than 20%. C, the loads are uniformly distributed. And D, the ratio of lift to that load is no more than 3. And E, the slab has uniform thickness. So when you compare the theory given here with the solution proposed, you can find that the correct answer is D. The ratio of lift to dead load is no more than 5. Here is the second practice problem. A two-way slab supported on a column grid without the U of beam is known a flat slab, flat plate, drop panel, wapor slab. So when you see the definition of the theory that I have shown before, the good answer is a two-way slab supported on a column grid without the U of beam is known a flat plate. The correct answer is B. In this slide, I show you a reminder about the reinforced concrete wall. In this slide, I show you the definition or the introduction of the non-bearing reinforced concrete wall. Otherwise, I give you some value for the minimum vertical reinforcement and minimum horizontal reinforcement. For the bearing reinforcement concrete wall, there is empirical method for the design, and there is also the trend design method. So when you have more time, you can see detail the theory that I recommend in this slide. In this slide, I show you the practical problem related to the reinforced concrete walls. According to ACI 318, the minimum horizontal reinforcement for the non-bearing wall is A, B, C, or D. So you can find in one documentation that ACI 318 section 14.33 give the minimum horizontal reinforcement for non-bearing walls A 0.002 times the gross concrete area for deform number 5 bar or smaller, and F sub Y is superior to 60,000 psi. B 0.0025 times the gross concrete area for other deform bar, or C 0.00 times the cross concrete area for smooth or deformed when did Y reinforcement lot larger than W31 or D31. So you can compare the theory with the option proposed. You can see that the good answer is C. Now, in this slide, I show you a reminder for the theory of the reinforced concrete footing. I show you in this slide some introduction about reinforced concrete footing, and in this part I show you the maximum and the minimum service soil pressure that are given by this equation. And here is the figure showing the general footing loading. In this slide, I show you some reminder about the factor load per unit length at failure, the equation corresponding, and the factor load per use. Otherwise, I show you the equation for the shear design. So here is the figure showing the critical section for shear in one footing. So when you have more time, you can see, you can take your time for the detail. Here is the practice problem related to the reinforced concrete footing. So the question is that the critical section are a distance d from the face of the column in what option? What is the option? So the solution is that for one-way shear, a single action shear or wide beam shear, the critical section are a distance d from the face of the column. So the good question, the good answer is B. In this slide, I show you a reminder about the structural steel for the beam. In this slide, I show you some type of steel beam, and this one show you nomenclature and terminology for steel W-shaped beam. And this one I show you some structural shape for steel beam. And this one show the typical combined sections. And in this slide I show you some equation, some main equation for the calculation of the fractural strength in steel beam. And this one show the beam bending blend for the bending about major axis, and this one for the bending about minor axis. In this slide, I show you some equation for the calculating the compact section criteria. And in this slide, I show you some equation for the calculate MP. So MP, it is the actual spacing between points of natural bracings. It is and for the most shape, LP calculate from equation 59.6. Okay, and LR is calculated from this equation. So in this part, I show you a figure showing the natural buckling in the beam, and this one present compression flank bracing using headed studs. And in this slide, I show you some equation for the effective radius of gyration. And this part show the theory related to the natural torsional buckling, so that you can calculate for the parameter request a available moment capacity, natural torsional buckling modification factor. So when you have more time, you can see the detail that I have written in this slide. And this slide show some processes for fractural failure, and this one show available moment versus unprecise length. And for this slide, I would like to show you some equation for the calculation of the shear in unstiffened beams. So now we part in the practice problems. So in this one, you can see that 25 feet long steel beam elastic uniformly at 4 kip per feet. Loading due to the cell weight is negligible, and they acquire adequate lateral support provided to the beam. The question is that what is the required plastic section modulus for the W12 shape using grade 50 steel? So for this question, for this problem, you can calculate firstly the required moment trend by this equation and use. And after, you can calculate the required plastic moment by this equation, and the required plastic section modulus is calculated by this equation, and finally you can find the result. And when you compare the final result with the option, you can find that the good answer is D. Now for the another practice problem. Here is the input data of the problem. A 15-feet long custom manufacture and roll continuous W14 time 60A shape beam is supported at each end and at each middle point. So with the input data, the question is asked, what is the most likely steel variety used in the manufacture of the beam, and whether or not the beam is compact? So for the solution, you can see that from the W shape, dimension and property table, for a W40 60A shape, the beam depth is 40 inch and the web thickness is 0.415 inch. So the nominal shear trend is calculated by this equation, and you can find that Fy is equal to about 42 kip per inch square. So when you compare the final result with the option, you can see that the good answer is C. And in this slide, I would like to show you some introduction about the structural steel columns. Structural members subjected to axial compressive load are often called by name, identifying their function. So the best known columns, the main vertical compression member in a building frame. Other common compression member include clothes in chassis and bracing member in frames. Here are some typical compression member cross section. And in this slide, I show you a reminder of the theory about the Euler column buckling theory. So you can calculate the buckling loading given by this equation, and after the buckling stress Fe is calculated by this equation. In this slide, I show you theory about the effective length Fe and the effective length approximative the length over which a column actual buckles. The effective length can be longer or shorter than the actual unprecise length. So for calculation Fe, you can use this equation. And here is the table showing some effective length factor K for some cases of structural of the structural steel columns. And in this slide, I show you the equation for calculating the slenderness ratio SR. SR equal to KL per R. And in this part, I show you the design compressive trend of the structural steel columns. So this figure show the available compressive trend versus slenderness ratio of the steel columns. So now we pass in the practical problems. You can see here the data of the steel compression member. A steel compression member has a fixed support at one end and a frictionless bone joint support at the other as shown in this figure. The total applied design load consists of a dead load of 7 kips, which include the weight of the member and an unspecified lever load. Design effective lengths are to be used, and they give you some property of the column. And the question is asked, this compression member is controlled by which type of buckling? So for this problem, you can firstly calculate the the unprecise length of compression member by this equation. Lx and Ly equal to 120 inch, and after that you can calculate the radius of gyration about the x-axis by this equation. Ax equal to the square square root e sub x per a, and you can find the result. After that, you can calculate the slenderness ratio about the x-axis by this equation. And after, you can calculate the ratios of gyration about the y-axis by this equation. And after, you can calculate the slenderness ratio about the y-axis by this equation. So at the end, you can calculate the limiting slenderness ratio by this equation, and you can find the result 113. So because this value 30.8, this one, the slenderness ratio y less than of this value, so that the column fails by inelastic buckling. So when you compare the final result with the option proposed, you can see that the good answer is C. Now we pass for another practice problem. A long column member has one end built in and the other end pinned. The column is loaded in compression evenly until buckling occurs. The question is that which statement about the column after buckling is true. So they give you 4 options A, B, C, D. So you can see that the built-in end of the column is completely fixed against rotation and translation. The pinned end of the column is free to rotate, but is fixed against translation. Therefore, the pinned end of the column experiences more rotational deflection, and the maximum deflection point is closer to the pinned end of the column. So when you compare the theory with the proposed option, you can find that the good response will be the B. Now we pass to another practice problem. A solid steel column with a fixed bottom support and free upper end is concentrically loaded. Material and geometric properties are shown in this figure. The question is that which is the available axial compressive design stress? So for response for the response of the practice problem, you can calculate firstly the least ratios of duration applied equal to R square times A, and you can calculate the R square root of the duration E week per 8, and you calculate you can replace the formula by this equation, and you can find the final result. R equal to 1.73 inch, and the effective length factor key is 2.1 for the given column and supported condition. So you can calculate the slenderness ratio by this equation. KL per R. So you replace the value of R ici. R you find in this equation. You can put the good value of K and L, so that you can find the final result for the slenderness ratio. It will be it is 130. So from the AISC table 422, you can find that the available column trend for compression member with a slenderness ratio of 131 is 13.2 kip per inch square. So when you compare the final result with the different option proposed in the beginning, you can find that the good answer is 8. EA. Now we can pass in another practical problem. A steel column is built in at one end and free to translate and rotate at the other end. The column uses a 12 feet long W12 times 45 beam. If the U trend of the steel is 50 kips per inch square, the question is that what is the available design stress in the column? So for the solution, firstly you can calculate the value of the slenderness ratio of the column by this equation, KL per R, so that you can find the value equal to 155, and after that you can determine the available design stress by this equation. So you can find that the slenderness ratio is greater than this value, the available design stress. Therefore, the athletic buckling stresses is calculated by this equation, and you replace the numerical value of parameter in this equation, and you can find the final result of FE, the elastic buckling stress, that is given by the value 11.19 kip per inch square. And after you can calculate the available design stress by this equation, FCR equal to 0.878 77 FE, and the value is calculated and equal to 10.45 kip per inch square. So when you compare the final result of the available design trace with the different option in the beginning, you can find that the good answer is D for this practice problem. Now in this slide, I give a reminder of the theory about the tension member of the structural steel. So tension members occur in a variety of structure, including bridge and roof structures, transmission towers, wind pressing systems in multi-story buildings, and suspension and cable stayed bridge, wire cable, rods, I-bars, structural shapes, and build-up members are typical use a tension members. So you can see here some common tension member, and here I show you a few years for the tension member with unstructured row of holes. So in the party, I show you the calculation for the gross area AG. A sub G is the original unauthorized cross section area of the member, and the cross area of the plus. So in this figure can calculate by this formula A sub G equal to B times T. B it is the width and T it is the thickness. And in this slide, I show you some equation for the calculation of the next area of tension member. So when you have more time, you can see the detail. And I show you in the figure the tension member with structured holes, and the figure show the tension member with uniform thickness and unstructured holes. In this slide, I show you some equation for the calculating of the effective area without of length connectors. This equation show this equation the equation is applied for bolted members, and this equation is applied for welded members, and this equation is used to calculate the effective net area. So for the design trend, I show you in this slide some slide for the design trend LRFD, phi sub T Tn is superior to TUs, and with the value of the phi T depend on the nature of the tensile area under consideration, and the available tensile strength considering failure from yielding is given by this equation. The other thing, The available tensor strength considering failure from fracture is given by this equation. And after I give you in this part some variation for the calculation of Pn by the other equation. So you can see the detail in the AISC specification. So now we can pass in the practice problems. The practice problem is shown in this figure. A bonded steel tension member is shown in the figure with the value of Fy and Fu's. The question is, what is the most nearly the effective net area in tension for the placed? So for fracture, choose the shortest path with the along the line A, B, C, D. A shown in the figure. So the cross member width is BG. You can calculate BG, and after you can calculate the net area by this equation. AN is equal to BG minus sum of the H plus 1/16 and on time T. And finally, you can calculate the effective net area by this equation. AE equal to U A sub N, and you can find the final results 2.94 in square. So when you compare the final result with different option in the beginning, you can find that the answer for this practice problem is B. So now we pass another practice problem. In this problem, W-shaped member with U strand of 36 KSI, ultimate strand of 58 KSI, carries an axial lever tensile load of 420 kips. The members flank are bolted to a connection bracket. The shear lag factor for the connection is 0.9. The required net area based on the fracture criterion is most nearly. They give you 4 possible options, A, B, C, D. So for this one, firstly, you calculate, you can find the effective net area based on the fracture criterion. Phi sub T equal to 0.75. And after you calculate the ultimate value of T, TU equal to phi sub T times T sub N. This one equal to phi sub T F sub use A sub E. And after that, you can find the value of A sub E that is equal to 15.45 in square. And from this value, you can calculate the net area AN equal to AE per use, so that you can find the value of net area AN equal to 17.2 inch square. And when you compare the final result with the optional response, you can find that the good answer is B, 17 inch square. And now we can pass in the practice problem, another practice problem. N L4 times 4 times 3 per 8 angle make form A36 steel is used a tension member and that is shown in this figure. The angle is connected to a gusset plate with 5 per 8 in diameter bolts. The center to center bolt spacing is 3 inches. The distance from the centroid of the area connected to the plane of connection X bar is 1.13 inch. So the question is that what is the most nearly the shear lag factor? So here is the solution. Firstly, you can calculate the length of the connection for the bolted connection. This length is the distance between the outer horn list. L equal to 2 times 3 inch equal to 6 inch. So you can calculate the shear lag factor by this equation. U equal to 1 minus H bar per L, so that you can find U equal to 0.812. So you compare, when you compare the final result with the different option, in the beginning you can find that the good answer is C. So now we can pass in another structural steel element. It is beam columns. So what is beam column steel structure? Remember that it is acted upon by compressive force and a bending moment is known as beam columns. So in this part, I show you some equation for the calculation for the pressure axial compression. This equation is applied for the large compression, and this equation is applied for the small compression. And this is the pressure compressive force relationship in the AISC specification. So when you need, you can apply the equation for the pressure compression force relationship. And in this slide, I show you the equation apply for the second order effect deflection. So I suggest that when you have more time, you can see the detail on the equation and on the parameter that I have written in this slide. Now we can pass in the practice problems. W14 times 120 with the paper steel A 992. This beam has been chosen for carrying an axial lever compressive load of 140 kips and a factor 480 feet kips lever moment about the trunk axis. The unsupported length is 20 feet. Size weight is permitted in the direction of bending. K equal to 1. The compressive strength is 780 kips and the bending strength is 495 feet kips. So the question is that the beam column is subjective to what option between A, B, C, D? So here is the solution. Firstly, to determine whether the member is subjected to small or large compression, you need to find the ratio of compressive load to compressive strength by this equation. PR per VPN. This ratio is equal to 0.80, and because this ratio is inferior to 0.2, the member is subjected to a small compression. So after you need to determine if the member is adequate by this equation, and the value of this equation is equal to 1.06 because set value is higher than 1, so the member is inadequate. So that when you compare the final result with the option in the beginning, you can see that the good answer is C. So in this slide, I will show you another fatigue problem. W14 W14 times 132 beam has been chosen to carry an axial lever load of 160 kips and a maximum lever moment of 325 kips about the trunk axis. The unsupported length is 22 feet, and they give you the another value of KCM IX. So taking into account the second order effects, the question is that what is the most nearly the required pressure strength? For the solution of this problem, firstly, you can find the all layer buckling load Fe1 by this equation, and you replace the value of the parameter given in the beginning of the problem. You can find the value of P sub E1. The value equal to 2,970 kips, and after you can find the x axis pressure magnifier B1 B sub B1 by this equation, and the value is equal to 1.015. 57. So finally, you can calculate the required flexural strength by the equation MR equal to B1 M sub NT. And finally, you replace the value that you calculate before in this equation. So you can find the final result MR equal to 338.2 feet cubes. So when you compare the final result with the option in the beginning, you can find that the good answer is A, 314 feet cubes. Now we can pass in the another tutorial steel member, it is connector. So here I show you one introduction about the connector. There are two types of structural connector, rivet and bows. Rivet, however, rivet has become virtually obsolete because of the low trend, high cost of installation, and stone variability and other disadvantage. For the bows, there are two types of bows. The two types of bows used in the connection of the steel structure are common bows and high strength bows. So in this figure, I show you some typical bolted connection. In this slide, I show you some reminder of the theory related to the hole spacing and edge distances. So you can see in more detail when you have more times. And this slide, I report some measurement related to the bearing and slip critical connections. And this slide presents the available loads for the fastener. And this part showing the bearing trend of the connecting member at both holes. So you can see different equation for the bearing trends of connected member at both holes. I show in this table the nominal fastener stress for static loading for different type of connector. Now we can see the detail of practice problem. The connection shall consist of 11 grade A307 7/8 in diameter, both hole size are standard. The ultimate trend of the connecting member is 58 KSI. The connective member is 0.5 in thick. The edge clear distance is 2.5 inch, and the center to center spacing of the holes is 3 inch. So you can see in the figure of this connector. The question is that what is the available bearing trend per bolt per inch of thickness in the connection? So here is the solution for the problem. Firstly, you can determine the bore hole diameter by this equation. D sub H equal to D sub B plus 1 per 16 inch, and you can find the result of DH. And after that, you can determine with clear distance LC value control for the bolt, and you can obtain the clear distance in between the interior holes LC equal to S minus D sub H, and you can find the result. This value equal to 1 per 16 inch. And after that, you can calculate the smaller value for the clear distance control, and you determine the available bearing strength by this equation. Phi times R sub n equal to phi times 1.2 LC times FQ, and you can find that this value equal to 107.7 kip per inch, and this group give 91.35 kips. So because of this value in not inferior to this value, so we can conclude that since the available bearing strength determined by the clear distance is larger than the available bearing strength determined by the both sides, the smaller value control, and the available bearing strength is 91 kips per inch. This value may also be determined using AISC table for a center to center spacing of 3 inch, a connected member strength of 58 KSE, and both sides of 7 per 8 inch. So when you see the result that you have about found here, you can see that the good answer for this problem is C, 91 kip per inch. So you do attention that it is not inferior but superior, 107 superior that the value. So now it's not inferior but superior. Okay. So we can see another party problem. A connection is made from 3 per 4 in both in parallel placed on A.5 in wide steel bar. The bar is 1 inch thick that has an ultimate strength of 65 KSI. The hoses are 3 inch from the centers to the side of the bar and 2.25 inch from center to center. Both hole size are standard. So the question is that what is the bearing resistance of the entire connection? So you have here 4 possible options. So the solution for this problem, firstly, you can calculate the hole diameter using the bowl diameter and standard clearance by this equation. DH equal to DB plus 1 per 16 inch, and you can find the result. And after that, you can calculate the clear distance between the interior holes by this equation. NC equal to S minus DH. And you can see the result of the LC. After that, you can determine the clear distance between the hole and the edge of the steel bar by this equation. LC equal to LE minus DH per the 2, and you can find the result of L sub C. And you can use the smaller clear distance since each bolt has the same property, so you can calculate the available bearing strength for one bolt by this equation. R sub n is minimum between two values given by the equation, and after that you replace the numerical value of LCFU or DBFU in this equation. You can calculate, and you can find that R sub n is minus between two values, and this one is equal to 84 kip per inch, so that you can calculate the available bearing strength by this equation. Phi R sub n e to the sum of phi R sub n times t. So for both two bolts, you can calculate the final result. This value is the available bearing strength is equal to 168.2 kips. So when you compare the final result with the option in the beginning, you can find that the good answer is C. So we have seen on chapter related to the structural design review that I have prepared. I know that there are a lot of the detail in the slide, but I would like to give you as much as possible the detail, and so that you can do the review of structural design. So my advice for the review of structural design is that, firstly, you try to do practice problems without looking at solutions. And secondly, if you have a question related to structural design, you can send your question to my email address, and I will answer your question as soon as possible. So good luck for your exam, and I hope that everything will be well for you. Thank you for your attention, and good luck for your exam.